Singapore. He's also one of the maybe the most prolific Scala open source contributor. He built a whole stack of systems, starting with the popular Ammonite REPL that is actually being merged into the Scala CLI now. The two are essentially feature complete, and I think Ammonite is going to be merged soon. The mill build tool, he will talk about that, and a whole stack of open source libraries from testing to pickling to web servers and so on. So please, Haoyi.
See if it works. Okay, that works. Let me just set this up. Okay, hi everyone. So my name is Haoyi, and this presentation is going to be about build tools. So the motivation for this talk is that build tools are kind of the messiest, dirtiest parts of most people's code bases. Like, you have your beautiful, pure functional like architecture, you have your object-oriented like a program, and then you have a bunch of bash scripts kind of wiring it together with some Python, with some Ruby, and with some Perl mixed in just for the heck of it. So even with your newer build tools like Scala's SBT or Maven or Gradle in other languages, it tends to become very messy, even though the languages themselves tend to be pretty nice. Like, Java is known to be very easy to learn. Maven Gradle is not. Scala is known to be very easy to program, but SBT is not. So this presentation, we'll talk about how some ideas from functional programming and object-oriented programming can really help simplify this build tool problem. We'll talk about why build tools are hard from a user perspective, kind of empirically, why do people have problems using build tools like Maven, Gradle, or SBT. We'll talk about why build tools are hard from an implementer perspective, like why haven't people just gone and made a better build tool and fixed all the user-facing problems. We'll talk about one of my open source projects called Mill. Mill tries to make progress in these areas, and we'll see what it's able to do. And this idea of functional and object-oriented builds, which I think is why my Mill project is able to make progress where other build tools have really struggled in the last 10 or 20 years. So just a bit about myself first. I've been working on open source projects in Scala since about 2012. There's a short list here that's a bit incomplete, but gives you a flavor: the REPL, the build tool, serialization, file system, HTTP, all sorts of libraries. My professional expertise is in developer tools. So I've worked on everything that happens before your code goes to production, whether your dev environment VM, your IDE integration, CI system, integration testing system, and lastly, the build systems, which is a topic of this talk. So I'm the author of the book Hands-on Scala Programming. If any of you want to learn Scala, it's a good book. Go read it. So first, let's talk about why build tools are hard from a user perspective. So in Scala, most people use a build tool called SBT. It's an extremely powerful build tool, extremely flexible. It can be very performant if used correctly. And the last thing is kind of the crux of the matter. Like, it's quite hard to use SBT correctly. And often, if you don't use it correctly, the performance kind of is poor, ID support's not great, and the extensibility model can be quite challenging. As Oliver mentioned, we have Scala CLI now. That's a good alternative for small projects, like one file, maybe two files. Once you have 5 files or 10 files, it becomes out of scope. So just the example of the challenges using the SBT build tool in Scala ecosystem. Just running SBT is quite unlike any other command line tool you've used in the world. You don't just run SBT through from the command line because the performance will be poor. So you open up SBT shell, you need to make sure it's run. There's a whole documentation page about managing this shell. And this is all separate from what you actually want to do, which is build your project. Like, I don't want to learn SBT, I want to learn to use my project and just have the build tool get out of the way. Another thing that I hit more recently was I wanted to try parallelizing some tests in one of my projects that I was working on that used SBT. And it took me 2 hours to turn on test parallelization, and I ended up giving up. So you have parallel execution in tests, which is what you normally use. You have concurrent restrictions, which you may also need to set, but you also need test fork parallel, which is separate from parallel execution, which has a separate set of concurrent restrictions. And then you have your test grouping, which may or may not make your test suite slower, depending on the exact kind of runtime characteristic of your test suite. So no one's going to help you with this. I had to get help on Discord after I gave up. But in general, it's a lot more difficult to do things that you'd expect not to be that difficult in SBT. Another area that build tools often fall short is IDE support. I can show you this in SBT, but this actually applies to almost every build tool. Maven, Gradle, Bazel all have the same problem. So if I look at, for example, the Gatling code base, Gatling is an open source load testing framework built on Scala. It's built using SBT. Here it is in the terminal. Can you guys read this code? Yes? Barely? Okay, bigger. So it has 20 submodules. You can see the SBT build files here. There's syntax highlighting. I can jump around a bit. But if you try to jump to the wrong place, like here, let's say you didn't know what library dependencies was, you'll find that there's nothing helpful. I can't find usages. I can see it within my own project, but where does it actually get used within the build system itself? Like, what if I modify this? What happens? How can I find out an IDE? I just cannot. And if it is very different from if you look at the actual Scala or Java code in this code base, let's say I pick some random part of the code. Maybe this is not such a helpful one. Let's look at this one. So like anything here, I expect to be able to jump to definition, even things in the standard other classes, aliases elsewhere, even in the standard library, I expect to be able to jump to definition. So in any Scala, Java, Kotlin, nowadays Python, or Java's TypeScript code base, you expect to be able to navigate around in your IDE, even when the documentation is not there, even when documentation is out of date, even when ChatGPT cannot help you, your IDE is meant to be able to help you find your way around. And you can do this in the Scala code here, but you cannot do this in the Scala code in SBT. Like I jump to SBT spotless and I get nothing. So why is that the case? The basic problem here is that when I look at things like library dependencies, this is really just a global mutable variable. You can see that if any of you use global mutable variables in your application code, you know that jumping to a global mutable variable, you get the type signature, and you get nothing else, right? Because anyone could be setting it, anyone could be reading it globally, and the IDE, just like humans, aren't able to figure out where the data is coming from or where it's going. So just because in SBT we wrap the global mutable variables in this setting key monad interpreter thingy doesn't make them any less global or any less mutable. And that's why IDEs, even though it's the same IDE and the same Scala language, are unable to navigate around SBT code, even though they can navigate very well around the rest of your Scala code base in the same project, in this case, Gatling. So that's IDE support problem. I showed you SBT, but really it's a general problem. You open up Gradle, try to jump to definition, you get stubs. Open up Maven, try to jump to definition, you get XSLT, again, stubs. So even though these build tools all have IDE support, the IDE support is relatively poor. The last thing I'm going to talk about is extensibility model. So every build tool has a bunch of built-in features, hopefully it does what you want. If not, every build tool has plugins, hopefully it does what you want. Again, you often will find things that plugins cannot do or plugins don't quite do the way that you'd like them to do. And every real project has some special stuff. Like your web server, like the Netty code base, may have some C code it needs to compile using GCC or Clang. Or some other projects may need to do bytecode mangling or special package formats or so on. So just as a straw man example, let's say I want to count the lines of code in a project and save it in a line count txt file to be used at runtime. Just an example thing that people may want to do. But doing this using SBT is not impossible. Here's an example snippet that I managed to come up with. But surprisingly challenging. Like, the thing on the left is that you expect like a new grad to be able to do it in about 30 seconds. The thing on the right will take a lot of fiddling. You may ask Google, you may ask ChatGPT, they may get it wrong, you may fiddle around some more. And in the end, you get something that you're not really sure is right or not. And you hope it works, and maybe it does, but also maybe it doesn't. Like if I ask any of you, is this correct? Who can give me confidence and say, yes, this is correct? Like, it looks right? Like, but if you look at the business logic or build logic, it is correct. Like the build logic is basically trivial. Docs, single line to count the files, write it to a file. This is correct. But the other stuff that I'm sure most of you would have trouble with, like, do you need def.task here? Do you need the task value here? Should line count be in compiler? Is line count okay to not be in compiler? Should it be in this build? That's very hard to figure out, even if you're an expert with Scala and even if you've used SBT before. And it's not just a problem with SBT. So here's an example Maven implementation. And this one is not correct. And let's give you 30 seconds if anyone can figure out what's wrong with it. So this is uses a Maven XML plugin, exec plugin, configures Maven to run sh-c to count the lines of code using find, pipes it to word count-l, which does a line count rather than a word count, and puts in line count.txt. Okay, so this doesn't work on Windows. Any of you who use Windows here, it's not going to work because Windows doesn't have sh. Any other bugs people can spot? And which is the most simple configuration of one of the most common build tools in the world. We forgot to escape our XML ampersands. We also forgot to escape our caret here, our pipe here. This pipe also needs to be escaped. So yeah, this is a problem. Same thing happens with Gradle. In this case, I have a Gradle build that does the same thing. It's complicated. And again, there's a bug in it. I'm just going to tell you the bug because you guys are not going to spot it. The bug here is we are depending on the wrong set of input files, which would mean that this task would rerun if you touch anything inside source main, even if it's not inside source main Java that we care about. So if you touch source main templates or source main resources or source main config, it'll rerun this task even though the output is the same. And there's no way for you to test this because the output will be correct. It'll just be non-deterministically slower sometimes for a reason that no one in your team or no one in the world will be able to figure out. And so these problems with SBT, Maven, or Gradle, the challenges of configuring the build tool are why people are often so reluctant to do anything with the build tool. You will screw it up. No one will be able to catch in code review. Your plugin authors will screw it up. That's why your plugins sometimes are buggy or sometimes don't work well together. And that's why build tools have a reputation for being so fragile and so hard to work with. So that's the build tool problem from a user perspective. But if build tools are so problematic, why don't people just fix them, make a better build tool, and get on with your life? And the answer is that build tools are quite problematic from a implementer or designer perspective as well, not just from a user perspective. So every build tool starts off simple. For example, this is an example from the JBang project, which lets you run a single file Java application with some dependencies at the top. Just have some magic comments saying that I depend on the library, I depend on this Java version. You run JBang, it'll download the library and run your single file Java code very easily. But most programs are not so simple, and most programs need more configuration. So instead of having a flat list, maybe we'll have like a very big list of configuration values. Maybe you end up putting in some kind of hierarchy to keep things neat. And that's how you end up with something like this GitHub Actions config, where GitHub Actions can be thought of as a build tool / CI system of sorts. You see it's a bit neater than having a huge list, even though it has quite a lot of configuration in it. And it's using a YAML syntax, which is also very common in the build tool. So it's equivalent to JSON, but with a few less curly braces. But if you look at this a bit more closely, it's not really a hierarchy if you look at this config. I'm like defining variables, and I'm passing them into what looks like a function that you can call, and I'm using the variable in the function body. I'm defining a job here, and I'm referencing it here. I'm defining a shared template here, and I'm referencing it in these two other jobs. So although many of these build tool configurations look like a tree structure, it's in YAML, or it's in TOML, or it's in JSON, or it's in XML, in reality, the thing you actually care about is not the tree, but the graph. So that's what makes build tools complicated. Build tools, in general, are really ways to do these templated graph computations. Like, for example, in the bottom, you have an example Scala/Java project with 3 modules. Each one has an assembly task, each one has a compile task, but kind of wired together in the graph. They look similar in each module, but not quite the same. So we need a graph because we need some way to order and parallelize the build steps. They need to be computations because class files or jar files or compilers don't invoke themselves. Someone in Bash or Java or Scala or Kotlin needs to specify how these things are created at each step. And needs to be templated because the different modules in the build will often look very, very similar, but are not quite the same. So lots of ways to model this. We saw GitHub Actions had needs keys defining a graph, Bash snippets to define the computation, templating using curly braces. Maven will have its own thing with library dependencies and so on. Some tools try and hide this in plugins, but the problem doesn't go away. If the build tool is hard to work with, the plugins will be buggy because the plugin authors are just humans as well, and they'll have problems working with the build tool. And this results in a lot of challenges making a build tool. So this is a short, incomplete list of questions that the build tool needs to answer that is unrelated to anything that you care about the build tool doing. So ignoring Java, Scala, class files, compilation, ignoring assembly, ignoring dependency management. A build tool also needs custom tasks, CLI syntax, task kind of data passing between tasks. How do you customize existing tasks because you will want to do that? How do you define task dependencies? Do you use depends-ons like we saw with Gradle earlier? All of these questions are necessary to answer, and if you look at, for example, the Gradle config we saw earlier, the complexity of this Gradle config that's so error-prone basically maps one-to-one with the complexity of the domain of the build tool. So build tools need to do this. Gradle needs to do all this too, and that's why Gradle is complicated. It's not because they want to make it complicated, but in some ways they didn't have a choice if they want to model everything a build tool needs to do. And this is, after that, you have to look at the things that you actually care about the build tool doing, like resolving dependencies, compiling source files, zipping things to make jars, all things which are very side effect heavy, just full of side effects, writing to disk, pulling from network, all things that don't fit well within a normal object-oriented encapsulation or functional programming purity model. So that's why build tools are hard for implementers. Like if I ask any of you to make a templated graph computation API, it'll probably be a very complicated API because templated graph computations full of side effects are inherently very complicated. So next, we'll talk about one of my open source projects, Mill, which is a build tool that tries to make progress in this area. So Mill is an open source build tool. It targets the JVM languages, Scala, Java, Kotlin. There's some experimental Android support. Someone's adding Groovy. It aims to be a lot easier to use and faster than most of the other build tools. It's used quite broadly in the Scala ecosystem, not the majority, but there's a big subset, including Scala CLI that we mentioned earlier, Corsair, the guys doing hardware design with Chisel all use Mill. There's documentation at millbuild.org if anyone wants to check it out. Mill build files are written in Scala, you see on the left. Even if you're not familiar with Scala, hopefully it doesn't look too foreign. There's packages, imports, objects which extend classes, methods. The only thing that you might want to know is methods are defined using DEF if you haven't used Scala before. And it's run using this /mill bootstrap script, similar to /maven w or /gradle w you might have seen elsewhere. So you can say compile, run, test, assembly, run the assembly later, all the standard build tool things. So the standard build tool things aren't so interesting, but let's talk about how Mill tries to improve upon this in terms of making the performance easier to get, in terms of the ID support, and in terms of the extensibility model. First, performance. In order to compare performance, you need the same project built using multiple build tools. You can't really find that in the wild. So just as a proof of concept, I ported the Gatling project from SPT to Mill. Got all the tests passing. It's not a small project, so it took about a day or so to port. But this is quite a realistic port. Like all the flags are set up correctly, dependencies set up correctly, sources, and so on. And what we realized comparing SPT and Mill is that SPT really has two different performance profiles. If you use SPT cold from the command line, which is how you use every other command line tool in the universe, the performance is really poor. And if you use SPT hot by opening this REPL, the performance is actually quite good, but you have this human overhead of managing this stupid little REPL. Like if you control C, you need to get back into it. If you change the build config, you need to remember to reload it. All these annoying bookkeeping things that you'd wonder why a computer can't just do it for you. And that's basically what Mill does. So Mill is similar to SPT. Mill does have cold start problems. It runs on a JVM after all, and JVM is known to have cold starts. But Mill manages this background daemon on your behalf. So you always get the performance similar to the hot SPT performance, but you don't need to jump through hoops yourself to get it. You just run Mill something from the command line, and Mill will start the daemon, reload the daemon, restart the daemon as necessary. Like it's not rocket science, but Mill does it and makes working with it just a lot more pleasant and easier. Other areas that Mill tries to improve upon this is large code base support, so things like supporting multiple languages, things like working with very large numbers of submodules, so even if you have 500 submodules, Mill doesn't get slow, whereas SPT tends to get quite sluggish at that point. Selective testing, where you make a change and Mill will do a breadth-first search in the module graph and only run tests downstream of that code change. So this is very easy to set up in Mill and can really save time and money on pull request validation. It's possible to do with SPT, but usually can be quite tricky and manual to set up. Last thing to mention in terms of performance is the build profiles. So the question everyone asks about their build tool is, why is it taking so long, and are we done yet? And SPT, Mill rather, generates this profile for every command you run. So if I go to, let's say I go to my Gatling code base, and I do a Mill clean and Mill compile all, Sorry, I might make this bigger. So every command you run in mil generates this out/mil chrome profile.json file. So this is a standard format defined by the Chrome team at Google. You can Google Chrome tracing format. And if I open up my Chrome browser, I can go to chrome://tracing. All of you can do this. All of you already have Chrome. So any of you can go to your chrome://tracing UI and get a page where I can dump Chrome profiles in and see exactly where the time is being spent. So in this case, for example, it took about 24 seconds to clean compile the whole Gatling code base. And the question you may ask is, hey, is that good? Is that bad? Am I actually using all my cores? Am I bottlenecked? And of course, you can squint at the terminal and try and see what's happening. But what mil makes it very easy to do is it lets you see just every command you run, where did the time go? I was bottlenecked on Gatling core here. I was well utilizing all my CPUs here. I got bottlenecked on Gatling test here, and so on. And from this, you can take action to improve things without having to be a build tool expert. Even if you know nothing about mil and you know nothing about the Gatling code base, hopefully you could have some ideas of this, of what you can do to improve the build time if you wanted to do so. Like maybe I can break up Gatling core to parallelize it, or break up Gatling common to parallelize it, so you can run in multiple smaller submodules that can compile in parallel. So that's a performance angle. I think it's pretty neat. It's just easier to get performance. Nothing I showed you is impossible with SBT, Maven, or Gradle, but they're difficult enough you probably won't do it. You probably won't set up selective testing. You probably won't set up build profiles. So you kind of just suffer with a build tool that's slow and flaky and you don't know why. Whereas mil makes it easy enough that you can easily figure out what's going on so you can get the best performance out of your build tool without too much effort. Next area I'm going to talk about is the IDE support. Mil has better IDE support than any other build tool. And let me show you what I mean by that. So let me pull this up. So core. So over here on the right, I have the mil build config for the Gatling core submodule. And on the left, I have the SBT build config for the Gatling core submodule, one of the submodules within the Gatling project. So the first thing you might realize is that although they're spelled a bit differently, like one uses lazy val, one uses object, one uses equals, one uses extends, they really have the same information. Like core depends on netutil, depends on quicklens, depends on common, also as a test dependency, depends on JSON path, also as a test dependency, and so on. So this module requires this configuration to set up, and mil is no exception. We need to pass it in. Where mil is different is that while SBT configures things using these global mutable variables where you jump to them and there's not much there, mil configures things using method definitions and overrides. So for example, let's say I override this key fork args equals, I don't know. And let's say I didn't know what this is, right? Maybe I'm new to the project, maybe something's misbehaving, I need to figure it out, maybe it comes from a plugin that's not well documented. How do I figure this out in mil in the IDE? Well, like any method, I can ask for its type signature and name. You can see here it says sequence of strings. I can also get its documentation. You can see here any command line arguments into pass to fork JVM. But let's say I want to learn more than that, like if something's going wrong. I can also see that this is an override. IntelliJ also knows that this is an override. I can jump to the overridden method. I can see the value that was there before I overrode it. This is something I did not get in SBT. I can see it was previously an empty sequence in this case. And I can also find usages in my IDE and see everywhere in the build system that uses this kind of configuration. So I'm setting fork args, but I don't care about setting fork args. I want fork args to do something else, and I want to see what fork args is doing. In SBT or most build tools, it's basically impossible. You go to like library dependencies here, and there's nothing. Whereas here, I can see that, well, if I search for fork args gets used in runner gets used in run background task, and run fork task gets used in run. So just like that, I can navigate around the build pipeline, just like I can navigate around any Java, Scala, Kotlin application code. And if something's misbehaving, I can figure out what step it's happening at and what's going on and what may be going wrong. I show you navigating downstream. I can navigate upstream as well. Like for example, let's say I look at this final main class thing here. No documentation. There's a type signature, but no docs. I jump to it, again, no docs. In most build tools, you'd be totally stuck here, ask ChatGPT maybe. Here, at least I have the implementation, and I can see that this basically delegates this final main class opt thing. And let's say there's no docs for that either, which there isn't. Again, in Mill, you're not stuck because even though the name may not be too clear and there's no documentation, I can see what the implementation does. For example, it delegates to main class. This says any explicitly specified main classes defaults to none. If there's one, I use it. If there's none, I call all local main classes. All main classes detected. So this one uses this class graph project to look at your class files and search for public static void main methods that look like main classes. If it detects an empty sequence, it reports an error. If it finds exactly one main class, it uses that. If it detects multiple, it reports like another error, saying, oh, we found multiple main classes, please tell me which one you want to use. So what's interesting here is that this is the experience that you get day in and day out in all your application code. In your application code, you never have good enough documentation. Application code is all proprietary, it's not on Google or ChatGPT. But nevertheless, because you have an IDE and because it's a strongly typed language, you can navigate around your application and figure things out even when things go wrong, even when things are not perfect. Whereas in most build systems, you basically have copy-pasting things and praying things go well, because when things go wrong in most build systems, there's no tools for you to help figure it out. Well, Mill brings the application code experience to your build tool. So that in Mill, if you're not sure what something's doing, you just navigate around your IDE, upstream, downstream, up and down the dependency graph or call graph, just like you would in your application. So you never get stuck, you can always figure out what's going on. That's IDE support angle. Last thing I'm going to talk about is the extensibility angle. So I think what's interesting here is that where most build tools require extensions to be published as plugins, Mill lets you just write code and import libraries to use in your build directly. And what does this mean? Let me show you. So over here on the right, I have the minimal Scala build using Mill. So it uses Scala, in this case 213, in the foo submodule. It's a Scala module, and that's all. So I can do like mill, ./mill foo.compile, for example, and it will compile my build, my project. But let's say I didn't want the defaults. Let's say I wanted to do something special. Like let's say I wanted to count the lines of code in this project and add it as a line count txt file. So in Mill, tasks are just methods, and every custom task is just a method you define. So I can define a method called line count, which is a task. I can call other methods within it. For example, I want to call all sources or all source files. If you're not sure, again, you can ask your IDE. The IDE will help you along. And I can map it to, for example, file.path, os.read.lines, .size, .sum. So that's all I need to do to define a custom task in Mill. It's just a method that's wrapped in this task block, calls other methods, and returns a value. I can now do mill show foo.line_count. It might take a moment to compile the build again. 17 lines. I can do mill inspect foo.line_count. You can see we automatically capture the Scala doc for you, automatically capture the line number, file name for you, all that stuff. So this is my custom task in Mill. Very easy for you to write, if any of you know how to write code. But we haven't wired it into our resources yet. So in Mill, resources, again, are just tasks. Tasks are just methods. And the way you customize a method in any object-oriented program is by overriding it. So I can override def resources. Again, you're not sure which one to override. You can ask your IDE. I can say, well, I want to keep the super resources so I don't throw away my resource folder. But I also want to write to my task.destination folder, which I'll explain in a moment, my line count as a string. And I'll append this reference to this to my resource path. So let me show you this, mill show foo.resources. So you may ask, what is this task.destination folder? So the task.destination folder is important because in any build tool, the world's biggest global mutable variable is a file system. Everyone's just reading or writing all over your file system. You don't know who's reading, writing to where. If you parallelize it, they may stomp over each other. If you delete something wrong, you don't know who's going to be affected. You can't easily clean your caches because of that. And that's why you end up with things like in Maven, you call Maven clean installed on every command you run because you don't know what's going to run on what order. So in Mill, the way you work around this problem is instead of a global mutable file system, every task gets this resources.dest folder. In this case, output/foo/resource.dest corresponds to task.dest here. And this is a locally mutable file system within the task that is globally read-only. So rather than a global mutable file system, you end up with some local encapsulated mutability, but that's pure with regard to other tasks trying to use it. And that makes things much easier for the build tool and humans to reason about it. So now if I look at my out/foo/resources.dest, I can see my line count txt file, and I do mil foo.run. I can see my application is able to pick it up, and in this case, it's printed out at runtime. So let's take this one step further. Let's say I want to use a third-party library. Again, a common use case, just as an artificial requirement, let's say I want to render my line count as HTML. So Mil doesn't have HTML rendering libraries built in. So if I try and do this from the command line, you'll see it yells at me saying, hey, I don't have this Scala tags library to render HTML. What Mil does let you do is it lets you very easily import these libraries in the build header. So I can say commonly Haoyi Scala tags, I think I need 2 colons here, 0.12.0. Now, if I reload this, and if IntelliJ is feeling happy today, IntelliJ is not feeling happy, so I have to reload my IntelliJ. Let me do that in a moment. And reload this here. Okay, so now that I've reloaded this, I now have my Scala tags library just included as part of my build. So I can, for example, I can write another task. Def HTML snippet is a task that I call a div h1 line count, paragraph line count as a string, dot render. I can call this instead of my line count when I generate my resources. And now when I do foo.run, you can see that it's now generating HTML at build time using a third-party library along with some custom logic. This HTML is cached on disk. I can look at my out/foo/html snippet.json to see the HTML cached on disk together with some metadata that Mil uses for validation. And what's most interesting here is that when you look at this build config, it's basically a very boring object-oriented program. You have object foo extend Scala module. You have a bunch of methods calling each other. You have a third-party library, just a normal Scala tags HTML library. What you don't see is you don't see like special build tool APIs or plugin APIs. You don't see special like HTML rendering plugin or text rendering plugin or resource generation plugin. Because in Mil, even though there are plugins for many common tasks, if you want to do something special, you can just do the thing rather than trying to find some plugin on GitHub last updated 5 years ago that maybe does the thing for you but in a half-broken way. So that's the programmability angle. Earlier we saw how hard it is to detect any bug in your SBT, Gradle, or Maven config. But hopefully you can see in the Mil build, it's a lot clearer what this thing is doing, and hopefully it's a lot more obvious when it's correct, and also it'll be a lot more obvious if something goes wrong. You'll be able to catch it in code review or in testing. So that's this demo we saw live. Okay, so that's the user-facing improvements that Mil provides over SBT and other build tools. But the obvious question then is, well, why doesn't everyone else have this? Like, Maven's been trying to improve these things for 20 years. SBT's been doing this for 15 years. Why haven't they managed to improve it? And I think what's been missing is this idea of functional and object-oriented builds that really underlies all these Mil features and user experience. First, this idea of build graphs as pure functional programs. Basically, everything a build tool does, 99% of it, is do things to inputs to make outputs. There will be some weird edge cases where you have to mutate your inputs, like if you're reformatting your source code, okay, you have to mutate the inputs. But most of the build tools, actions, you don't touch the inputs. You only make a new output that is separate. And if you look at the things we saw earlier, all these seemingly side-effecting IO-heavy actions, downloading from network, code generating, reading, writing to disk, all of which can basically be thought of as pure functions. And yes, you have to read and write to disk, but as I mentioned earlier, you can kind of treat the disk as pure if you encapsulate the mutability, so only I can write to my folder, and you guys can only read from it. And from your perspective, you can basically treat it as a pure functional disk where I get this file from someone upstream, and it's a read-only file, it's immutable value, and I can't touch it in any other way. And all of these actions you see here, assembly jars, class files, test results, all fit into this mold. And what's interesting about these pure functional programs, pure functional build steps, is that once you get rid of this global state, global file system, you end up having these tasks that only read their inputs, only return their outputs. Both of these can be files on disk. But once they're functional, they can be parallelized, cached, and scheduled very easily both by humans but also by the tool. So the tool can say, hey, you three run in parallel. I know you're not going to stomp over each other's files on disk because you all have separate folders to write to. I know you're not going to mangle other people's files and have race conditions because all other folders are read-only to you. So Mill can do this because these tasks are pure functional, and therefore can do this on your behalf without you having to deal with executors or locks or scheduling yourself as a build tool user. And pure functional programming, again, is what makes jump to definition in IDEs useful. If you have a global mutable variable, like in this case in SBT, you jump to it, you get a global mutable variables type signature, maybe it's docs comment and nothing else. Whereas if you have pure functional tasks, I have all source files, I don't know what it is, I jump to it. I don't know what's all sources, I jump to it. I don't know what sources, I jump to it. I don't know what's find source files, I jump to it. In a pure functional program, every jump to definition is useful. And that's what part of what allows Mill to have so much more rich and IDE experience than we saw earlier with SBT, or which you would see in other build tools like Maven, Gradle, or Bazel. So that's build graphs as pure functional programs. Like people often think build tools are these sketchy things full of side effects and bash scripts, but with not too many changes, you just put your side effects within a nice encapsulated folder and treat it as read-only from everyone else. You can really treat your build tool as a pure function, as a bunch of pure functions with all the benefits that entails in reasonability, scheduling, and other things, parallelizability. The other thing I'm going to talk about here is the idea of object-oriented build definitions, which I also think is very unique in the Mill build tool. So earlier on, we talked about this idea of templated graph computations, how every build tool needs to do it, whether you're writing XML in Maven or Groovy in Gradle or pseudo Python in Bazel or just bash scripts. And pure templated graph computations are complicated, so if any of you try and come up with a templated graph computation API, it'll be a very complicated API. So what do you do about it? Well, it turns out that everyone here already has this way they've been writing templated graph computations for the last 10 or even 20, 30 years. And that's called object-oriented programming. So object-oriented programming with objects, classes, methods, overrides, super, and other method calls are exactly a fit for a templated graph. And if you look at what this means, if I say object foo extends Java module, it's an object that extends a class. You all know what objects extending classes get. They get their methods, and the methods call each other. And if I add a new method, line count, that calls all source files, or I override a method, resources, that calls super and also calls line count, I don't need to teach you anything at all for you to know how this will affect the graph on the top right. You know how object-oriented programming works. You know how override and super works. You know that this stuff gets spliced in. You know assembly calls the new resources, that resources call the old resources, that call super. All of that you already understand without me having to teach you a single thing. And if I want to template the graph, I just take my object foo, which was a singleton, I turn it into a class or a trait in Scala, and I extend it twice in two different objects. Ta-da, I have templated my graph. And you can do other further things as you'd expect. I can have further customization in each of these objects. I can have subclasses, I have customization shared between objects. All your standard object-oriented techniques for managing your code running in these method calls and classes perfectly fits the common things you want to do when you're templating a build graph. And once you have the build graph, you can do things, Mill can do things like, oh, look at compile and line count don't depend on each other. And because we saw earlier that we can treat them as pure, we can run them in parallel. Every method has a name fully qualified, like foo.linecount, foo.compile, foo.assembly. So we can use a name from the command line without you having to have a separate method task name. We can also use a name to assign every task a unique place on disk to put its JSON metadata and its .destination folder for file outputs. And these are guaranteed to never collide, so that we can treat them as pure and kind of encapsulate the mutability within each individual task. And we can do incremental invalidation. For example, if we touch the resource folder, which is now called super because we overrode it, Mill can just do a breadth first search, see assembly needs to recompute, see compile and line count do not need to recompute. Mill knows where to get the old output for compile and line count because it's here on disk at a standard location, so you can reuse it. Mill knows where to find the old output for assembly, again at the standard location, so Mill can delete it and recompute a new assembly from scratch. And what's most interesting here is that in this case, you see there's no code on the left related to any of these things at all. You see, what you have here is a very boring object-oriented program with object extends class, method calls method, override super, all concepts that you probably learned in your first year of college or programming class in high school. What you do not see is you don't see depends on clauses, input, output, file registration clause statements. You don't see threads or mutexes or locks or semaphores or other concurrency-related things. You don't see cache key computation, cache invalidation. So Mill's able to squeeze all your user-facing code into an object-oriented model that's actually very simple for people to understand, and handle all the build tool-related stuff largely behind the scenes. And earlier, we saw this long list of things that, for example, Gradle needs to do, and how it corresponds to things that the build tool requires. Mill also needs to do all these things, but Mill squeezes it all into this object-oriented facade. Like, how do you define a custom task? Do I need to use a task.register callback with a string with the task name and a lambda block saying the body of the task that does side effects? No, I just define a method. What's a task output? Do I need to write it to some output somewhere and register it somewhere? No, I just return the value as a return value of the task. So all of these things Mill does handle, but it handles in a way that's much more familiar to anyone who's learned Java 101 or Python 101 like 10 years ago in school. So just to wrap this up, like the idea of object-oriented builds, your builds are just methods, objects, classes, extends, overrides, super. Everything works as you expect. Everything works as IntelliJ expects and VS Code expects. That's why the IDE support works so well just now. There is no Mill IntelliJ plugin. IntelliJ already understands how all this stuff works. Mill handles all the other things for you 99% of the time, which means you get good performance because you don't have people forgetting to cache things in their plugins. You don't need to clean because you don't have people screwing up the cache key computation in their plugins. You have more time left over to do other things like implementing build tool features, tooling integrations, or working your own application code. And in terms of tooling, talking about tooling integrations, we went and integrated quite a long list of tools for you in case you want to use them out of the box. But if there's some tools you want to use that are not on this list, hopefully it's not too difficult for you to integrate yourself, like what we saw earlier with the line count HTML plugin. So this is the last slide. And I think to sum up, if any of you who are curious about build tools or curious about how functional programming and object-oriented programming in Scala can be used for like a real-world use case, I think you should take a look at Mill and give it a try. Like, Mill not only has some very interesting ideas, this idea of functional object-oriented builds, which I think is quite unique within the build tool ecosystem, even outside of Scala. These ideas aren't just theoretical. They correspond to real-world improvements in things like performance, in things like improved IDE support, and in things like having an easier programmability model. So I think I have 1 more minute. So the docs are here. This is a mill-build website. We have getting started docs for Java, Scala, Kotlin. We have migration tooling and migration docs if you want to migrate. And if you want to take an existing code base, for example, if I go to if I go to the Gatling code base, I can just like curl down the Mill script and do Mill init, and it will do a best effort auto migration of the SBT build to Mill for you. So you can then, after that, you can run Mill compile, Mill test, and then it'll work. So I think that's the end of this presentation. Thank you for listening. We haven't tried, but we are trying. Yeah, so it hopefully might happen someday. Any other questions?
Yes, I have one. How will you convince people to switch over? I think one part of the story must be converting existing builds in the systems to your thing.
Yes.
Any ideas about that?
So yeah, I showed you just now. So earlier I ran ./mill init from the Gatling code base, which is here. I can now run mill under wildcard.test, and you can see it will compile and run almost all the tests in the Gatling code base out of the box. There's a few tests that in SBT they have special customizations that Mill's unable to automatically convert, but the vast majority of tests just rely on compiling code and running it, and with dependencies, Mill's able to run out of the box as you see on the left. So hopefully that will smooth the migration path, although it's never easy to migrate, but it'll hopefully make it less challenging. Yeah.
Okay. One other question. So you said that you don't need to handle dependency tracking, parallelization, it does everything for you. So how does it do it? So, because you just write an object-oriented.
Sure. So where's my slides? So basically, when you see like def resources equals def line count calls all source files, this is kind of like an async await transform similar to SBT or similar to like idiom brackets you see in like other languages, where we turn this task into an applicative data structure, and then the applicative data structure then you can inspect the data structure without first running it. So you can inspect it, schedule it, and then run it in whatever order you like. This works 99% of the time. Sometimes you have to customize it yourself. Like, for example, you may want to have some special cache invalidation logic to handle the Scala incremental compiler or the Kotlin incremental compiler. That wants to manage its own caches and isn't happy if you wipe out the cache every time you run it. So in that case, Mill does have some special like escape hatches to go under the hood. But most of the time, you can kind of just close your eyes and pretend it's like a pure object-oriented program. It mostly just works. Yeah.
Okay, let's thank the speaker again.